Good morning, everyone. Uh, Today is Ozen Engineering's webinar series. We'll start in just a minute. Okay. Today's topic is DC power designing ANSYS. It's about signal and power integrity. It's as usual. This is one of many Ozen Engineering's webinar series. We have a lot of webinars done before. It's available on our website. Feel free to visit our website to take a look at the resources and the libraries. Um, we are Ozen Engineering. We're a consulting company, and we are ANSYS channel partner. We also do consulting works for our customers. Um, if so, if you're interested, feel free to contact us through a phone call, through our email info@ozeninc.com, or if you are our current customer, send that have who has questions, send to support@ozeninc.com. So today's topic is about DC power design. So basically, it's a new offering that focuses on the PCBs and the gaining market share in the power electronics and PCB manufacturing market. Um, it is is using the SI Wave DC tool that which will gives you a low cost solution to predicting DC power distribution problems. Um, the solution can find current bottlenecks, predict high power losses, and also large voltage drops. Application examples. So it's a so the objective is just an entry level DC power solution. So it's not just for the CAE engineers, but for designers. It's also a very user friendly tool for designers. The purpose of this tool, the intention of this tool is just to give a a quick quote unquote scan of the board to give you an idea of your power design. So, as I said, it's an entry-level DC power solution. So all ICs require DC power to operate. It is common for layout engineers to inadvertently cause DC shorts and use too few vias when designing PDM. So, but so so with this problem that often occurs among the designers, the ANSYS offers this solution that uses SI wave DC to predict the performance, to predict uh, the power performance, the temperature plot, the temperature map. So it is also uh, there is also a bidirectional link with another tool of ANSYS. It's called Icepack to determine the thermal effects. So Icepack is a CFD-based electronics cooling tool. So there's a bidirectional link within the SI wave, which I'll show you just in a couple minutes. So the value of this simulation would be that the simulation of the DC power using ANSYS starts with design concepts, includes the full influences of manufacturing, and allows detailed evaluation of the power delivery network, signal net routing, and the connector, and the via breakouts. So that was the content on the slide. Um, the the images on this slide, if you look at the bottom of the slide, there's four images shows the meshes it has on the meshes it creates on a certain board. From left to right, it's initial mesh, after mesh after 3 passes, mesh after 10 passes, mesh after 20 passes. So as you can see, with the increase of number of passes, the mesh uh, gets denser. So the initial mesh is pretty coarse on on a lot of the areas. So uh, this adaptive meshing technology ANSYS has allows the software to automatically mesh your model for you. All you need to do is to specify the convergence criteria and uh, the number of passes. So here, well, 20 passes is, I would say, is a relatively large number. Usually 10 passes should be fine, should give you accurate results already. But as you can see, the 20 passes has really, really dense mesh elements on the details, especially as you can see in the middle of the board. So that's just one advantage of using ANSYS ANSYS technology, well, ANSYS electronic business units, and ANSYS electronics products, because automations are being taken care of. Uh, so as we were discussing before already, some of the ANSYS advantages in terms of accuracy, there's adaptive meshing, which was uh, which was what I was just talking about. In terms of speed, especially formulated solver for SI Wave DC. So SI Wave DC really is a 2.5D solver, meaning that it takes approximation in between the layers. So it's not a full 3D structure, a model structure simulator, unlike another flagship tool, HFSS, which is a 3D full structure simulator. SI Wave is only a 2.5D hybrid solver. So mm, with uh, with this compromise, quote unquote compromise, SI Wave allows a significant speed up in terms of getting you results fast. Some other advantages are user experience. Um, so so this ability to solve from a single environment, meaning that within the single GUI, a cell with GUI, there's a lot more things you can do. So this DC power design, this DC power design is one of many functionalities. SI Wave can include as many as say a signal integrity, power integrity, um, in frequency domain as well as time domain, SYZ parameters, I diagrams, bond wire analysis, so on and so forth. So lastly, just want to introduce a little bit about the different options we offer for this SI Wave product. So right now we're looking at SI Wave DC. It's a DC it solves your DC problems. It includes ECAD translation. With one notch up, it's SI Wave PI. It includes the PI advisor. That's another module be added on to the DC level. And then the last, which is the full level, the full comprehensive product is just called SI Wave. And it also would also include circuit simulation, which would allow simulations like eye diagram, uh, j- uh, j- eye diagram, transient analysis, uh, stuff like that. Okay, so let's just take a look at how SI Wave looks and what we can do in terms of DC power design. Right now, I have I have this board. Um, we are looking at the GUI right now. I would say relatively, it's a pretty clean and neat GUI, relatively user friendly. We have the layers on the left side. You can toggle them on and off. So this is all off, and then if I want just want to see the top layer, and you can select the components you want to see in the layer: planes, traces, pads, vias, and circular elements. And also we can toggle on the bottom layer, and this is just to make the elements solid or sketch. So a we have a board like this. Um, so we want to do a DCI simulation to see how the voltage distribution looks like on the board, how the current looks like, how the current and current density, where the current is going. So yeah, so SI Wave can do all of that. The general workflow is to firstly import the design. So we support a lot of different file formats, ODB++, DXF, GDS2, and Mentor graphics. So after we import the design, we will need to configure a DCR simulation. We'll have to specify a power supply as well as or current sinks. Then we basically just hit the hit the button for run, and we'll do the analysis, and then we just need to post process it. And we will need to configure a thermal simulation, which to specify whether it's a conduction or a convection, and then set up the PCB airflow boundary conditions. So we have this board imported. So let's see. We have a current sink on here. Here, I believe it's called U2A5, U4B1, and U25. So, so all the components can be seen here. The voltage source is, I believe, it should be right somewhere right here. PCB should be on the top of the PCB. There should be a. This should probably be where the right there we go. It's says U3A1. Right. That's where the voltage source is. That's the power supply. And then if we take a look at the bottom layer, this will be a current sink. Okay. Then we just need to configure a DCI drop analysis. So on the top, there is a SL Wave workflow wizard dialog. Every time you open the software, this wizard will pop up. It kind of walks you through the steps that you might need to take to configure a board. So from import a component file or import setup. After the import, it will ask you to verify a stackup, verify the pad stacks, circuit elements, power ground net classification, and sanitize the layout for simulation. After that, you can say you want to assign maybe a S parameter capacitor model or SPICE net list, blah blah blah. And then in this case, we want to configure a DCI drop analysis. So now we have this window open. So we want to specify the voltage source as well as your current sink. So we start with this. This is a voltage source, voltage of 3.3. We also want to select, let me see, V 3.3 S0, V 3.3 S3, and V 3.3 S5. J2. So so as you can see, as we place a check mark in front of these sources, it will tell you what the type of sources they are. So for example, this one, the J2L1 is a current source. That's a constant voltage. That says it's a constant voltage of 2.37 amps. And we have the following, just to make sure, kind of go through what they are. So this is an example project, so we don't need to make a lot of modifications on that. Then, so you could also check the save button to save a flow configuration file. So that will give you a .fcf file that you can use repeatedly for the same board or same analysis. Check and uncheck the hide RLC command to see passive devices. So you can see the passive devices that's connected to these sources. Then we can configure the simulation. Then we can click the once there's a check mark, we can validate it. I would say doing the validation, you can specify a number of cores to use to speed up your process. Okay. So now we just need to hit simulate. So SL Wave requires a global 0-volt reference location. It is automatic. It's usually automatically applied to the negative pane of the voltage source. So this will create a reference point for the voltage plot in the results. So that would be this one. Okay. So we have. So you specify the uniform design temperature. So let's see what else we can do here. Let's call this DCR simulation 0. And we already have an Icepack simulation. So we'll just launch it. Hexahedra. That's Um, okay. Something, some file is missing, but that is fine. We already have some results from before. So, after you successfully run the results, you will see you can see your results down here in the results um, panel. So we just did two simulations, DC air drop simulation and a Icepack simulation. So here you can specify what kind of results you want to see on the board. So we toggle all of them off so we can see that. Oh, I see. So we need to turn on these two to show the plot. There we go. So we can take a look at, say, the via current on the top. Also, maybe say current density on each layer, voltage, power distribution. Uh, if we turn them on all together, then this will be a very vivid picture. So the current density, we can see it's very heavy in the center where the voltage source is at. Um, what else can we show here? This is on. So let's take a look at the power layer. So, yep, on the power layer, this is what it looks like for the current density. Okay, this is what it looks like for the via currents. This is what the voltage looks like and power distribution. So for the via currents, um, the 0 and x represent the current magnitude between the layers. 0 meaning the current to the layer towards the top of the stack up. X is the current to a layer away from the top of the stack up. Okay. So after that, we can. So based on these, we can start another one for Icepack simulation. So supposedly we should be able to plot Icepack power map, but see something is. So what you need to do is that after a DCIR simulation, you will need to do a Icepack simulation. For some reason, this project never enables me to do another Icepack simulation. But the idea is that you click on Icepack, it will it will allow you to specify a Icepack simulation based on the DCR simulation you did, some simple specifications, and you just hit launch. You will be able to have an Icepack simulation. Then, with this, you will be able to display the temperature on the board. Then you can open the project in Icepack. It will launch a standalone Icepack, so you can work with coolings based on this. Let's see if this opens up. Yep, it is opening up. So yeah, this is the Icepack we're talking about. So yep, this is the so generally this is the DC power design workflow in SI Wave. If you have any questions, feel free to put that in question section here, or if you have any interests in this in the material, in the contents, in our products, feel free to reach out to our to our sales representatives. Okay. Without further questions, then this will be all I have for today's webinar. Okay. Thanks for your attention and have a nice day.